We'll go over the torque as a vector quantity, try to have a clear picture of what that means in our minds. So torque is defined with a vector cross product. So I have a position vector R cross F gives me the direction, gives me the torque as a vector. And let's remind ourselves a little bit about what the cross product does. I take two vectors, so like the position vector R and then the force vector F. Their cross product, R cross F, points in a direction that's perpendicular to both R and F. And it gives us a vector that is right-handed, in the sense of a right-handed coordinate system. So the vector R and the vector F, they're not parallel to each other. They're not pointing in the opposite direction. So they span a plane, right? Their cross product then points perpendicular to that plane, and it's going to point in the following direction of those two possible perpendicular directions. It's either basically out away this way or going into the page this way. So let's talk about how we find what direction it points. So you take fingers of your right hand, point it along the vector R, then curl the fingers of your right hand so that they're parallel to the second vector, which is F. And then the thumb of your right hand points in the direction of R cross F. So R cross F points this way. And so this would be a torque that is going to be circling around the Z axis. At this particular moment in time, it is pointed perpendicular to R, perpendicular to F. So it's partly coming out of the plane of the screen. And then that torque, you can imagine that acting over time to change the orientation of this object that has a force acting on it at the current position vector R. So direction of the torque comes from the right-hand rule for a cross product. The magnitude is the magnitude of the position vector, the magnitude of the force, times the sine of the angle in between them. So if the two vectors point in the same direction, then the angle is 0 and there is no torque. And if they point in opposite directions, then again, the angle is going to give you sine of that angle, sine of 180, 0, and no torque. But if those two vectors span a plane, they define a unique plane, then the vector cross product will give you the right-handed direction perpendicular to that plane. All right, let's try this out with a couple motivating questions. So I have a position vector of a particle is directed along positive y. What is the direction of the net torque acting on the particle if the net force is directed along the negative x direction? And you've got all of your choices. X, Y, and Z, positive, negative for each. So try that out as a vector cross product. Position is along positive y. The force is along negative x. The torque is going to point along what direction? So try that out, and then we'll work it out together here in just a bit. All right, so that gives you a torque that points along the positive x direction. So let's try to draw out a right-handed coordinate system. So I've got a positive x-axis, positive y-axis, and then right-handed coordinate system, z is pointing up. So he said that the position vector was along y. So there's r. And the force was along minus x. So there is r cross f, and we can work that out. So r cross f gives me a torque that's parallel to the z-axis. So it would point up that. All right. Position vector along positive y, force along minus x, r cross f. My thumb is pointing parallel to the z-axis. So I have a torque that's along positive c. All right, and then next question is to get us to think a little bit about the direction perpendicular to the plane and what that means. It does have a specific meaning. So I have like a hockey puck and a mirror hockey table. So it's a uniformly rotating object. If the object's angular velocity is a vector, in other words, it points in a certain direction in space, is there a particular direction we should associate with the angular velocity of this puck? So it's a linear velocity. It's tangent to the circle. The circle is its path, its trajectory. What's the direction, vector nature direction of its angular velocity? So think about what makes sense for that out of those 5 choices, and then we'll go over it together. So what makes sense for the nature of the angular velocity vector is that it's going to be along z or minus z. Then let's see why. At this particular moment, the linear velocity is along x. I come to a later moment as it swings around, it's going to be along minus y, minus x, plus y. Everywhere going around this circle, that puck is having a velocity that is some mixture of x and y directions that it's pointing. And so I could describe it as an instant in terms of what direction the linear velocity is going. But what makes sense as a unique direction to describe this motion is along the z-axis, either positive or negative. We'll get to which in just a second. As this puck is circling around, it is keeping a constant direction of being in the xy plane. Okay, and so let's see how we can ascribe this velocity in terms of the angular velocity. So there's a position vector right now to the puck, and there's its, make it a vector, its velocity vector. And if I have an angular velocity that is constant and pointing up, then what we can say is that v, linear velocity, is going to be equal to the cross product r cross omega. So I just need a position vector going from the rotation axis to where the puck is. Then I do r cross omega anywhere around that circle. It's going to give me the velocity that's tangent to the circle. And so this is part of like a coordinate transformation of going from an inertial frame to a rotating frame of reference. You pick up a part of your motion that's associated with the rotation of the frame. And this relationship for the motion of the puck will hold true if I have omega that is in fact constant in direction, constant in magnitude, just parallel to the z-axis. Then r cross omega will give me a vector for its linear velocity that's always going to be tangent to the circle and keep the same magnitude as long as the path is a circle and the angular velocity is constant. So this is the thinking for how we relate the linear motion to the angular motion, and this is how we get to a direction for the angular velocity. It's in terms of this underlying relationship that V is R cross omega, just like torque is R cross F.